Okay, let's get started. I hope you all had a good lunch, and I'm happy there weren't any tomatoes included in the lunch today. My name is Jeroen Frijters. I work on ikvm.net as a hobby. I've been working on it for 10 years. So ikvm.net is a Java virtual machine implementation for .NET and Mono. So I have quite a bit of experience in both the Java virtual machine and the .NET runtime. And I've encountered some issues, difficulties, challenges, let's say, with the Java virtual machine, and I've seen some alternative approaches in the .NET virtual machine, and I thought it might be interesting to talk about some of those today. It's a bit of a random collection of items. Please ask questions during the talk if you have any questions, so that I can expound on topics that might be interesting, because it's hard for me to gauge what's really interesting or not. I don't work for Oracle or Microsoft, so I don't have any big legal disclaimers or anything like that. I have some biases, of course, like everyone else. My biggest bias, I think, is that I am very partial to statically typed languages and ahead of time compilation. So you'll see that show up. And also I'm sort of a plumber. I like working on the low level stuff, but not in C or C++. I think that assembly is nice, bytecode is nice, but C and C++ really aren't that great. First, some terminology. CLI is the standardized name of the .NET runtime, the VM, basically common language infrastructure. And CLR is Microsoft's implementation of the same thing. And there's also Mono, which is also an implementation of the CLI. And then there's IL, intermediate language, which is the bytecode name. And it also is also known as CIL or MSIL, variously. And then there's this distinction between managed code and unmanaged code, managed data and unmanaged data that they make on the .NET platform. And it's kind of interesting. In the Java world, you would basically say we have managed code and managed data in the VM. And then outside of the VM, you have unmanaged data and unmanaged code. But in the .NET world, they can be mixed a little bit more because the .NET runtime also allows unmanaged data to be used from within managed code. First, a little bit of introduction to the type system. The primitives are very similar to the Java primitives, although there are a bunch more of them because they also have unsigned primitives. And byte, for example, is unsigned. I don't know, is anyone here who likes the fact that the byte is signed in Java?
It's great.
Oh.
That is just such a horrible thing. I still have nightmares from 1997 when we started working with that. And then they added something quite interesting, which is called int pointer, which is an int that is sized of the pointer of the machine you're running on. So if you're on a 32-bit architecture, you have a 32-bit int. If you're on a 64-bit architecture, you have a 64-bit int. So if you look inside OpenJDK, you'll see that long is used everywhere to represent the pointer. But on a 32-bit system, that's a bit wasteful. It's only 32 bits wasted, but still. And on .NET, they have this nice primitive type to express that in a better way. And then there's this weird thing called type reference, which I will not go into. And like I said in the previous slide, they have this managed versus unmanaged data idea. And this means that the .NET runtime supports unmanaged pointers, or managed and unmanaged pointers in managed code. So in managed code, you can basically just take a pointer to some unmanaged data that you allocate off the native heap and work with it. It's a bit like what you can do with unsafe in Java, except that it's part of the standard API, standard platform. You do need, of course, to be fully trusted to be able to do that, because otherwise you would have a security problem. And then there's arrays, which they call vectors, and they have multi-dimensional arrays as well. So not the jagged arrays that Java has, which they also have, of course, but real multi-dimensional arrays. In addition to the primitive types, there are also user-defined types, obviously, and user-defined value types in particular are very nice. I know John has been thinking about, John Rose has been thinking about how to add value types to the JVM, and they would be I think, a very good addition to the JVM. For example, to return the tuples without allocating anything, without boxing anything. There are some challenges with them. One of the big problems that I encountered on .NET is the fact that you cannot really use a value type to safely encapsulate multiple fields. That is sort of a weird issue that I think no one really realized at the beginning, but that eventually showed up. When you have a value that is composed of, for example, a reference to an object and an integer, and you copy that value, then of course these two fields are copied individually, and that is not an atomic assignment like a normal reference assignment or a normal integer assignment is. And it makes sense when you think about the individual fields, but when you look at it from an abstraction point of view, then you forget this fact. And this means that you can, when evil code is trying to attack you, they can actually have multiple threads mutating the same value, and then you can read the value from another thread, and then you can read inconsistent states. And this actually resulted in a security violation or error in .NET, where they had a value that had an array and an offset and a length in there, and they assumed, because in the constructor of the value type they checked that the offset and the length were in the range of the array, they assumed that was safe, but it turned out not to be safe because it's possible to, by using multiple threads banging on the same location, to create values that violate the constructor invariance. One thing that is particularly nice about value types, and it's going to sting a little bit here, I think, is that they work really well in conjunction with reified generics. If you have a dictionary, for example, then it's very efficient to create either keys or values that are value types if you want to have composite values or composite keys in your dictionary. And that is something that is going to be a little bit harder in Java. A nice thing about arrays in .NET is that they are derived from a common base class, system.array. Really, when you think about it, it's quite strange that Java doesn't do this, because if you look at system.array copy, taking object, immediately some alarm bells must go off when you design something like that and think, well, this thing only takes arrays, but why am I having to use an object type here? Why not add a common base class to arrays? And this includes some useful methods, actually. So you can do get value and set value, and for primitive types it will just return the boxed value. And that's not very efficient, of course, but in some cases you don't really care about that, and it's just convenient to have a common interface.
So it's not generified?
It is generified in the sense that arrays implement interfaces, generic interfaces. So, for example, if you have an integer array, it implements iList of int, but the base class is not generified now. That would sort of defeat the purpose, because then you would not have a way to say array, just any type of array. So if you look at array.copy, which is the .NET equivalent of system.array copy, it just says, I need an array, and don't really care about what type of array. And then it does the same types of checks that Java does, because you need to copy from compatible types, of course. But it's a little bit nicer in the type checking, of course, in the language than when you pass in you want an array that you can only pass in arrays and not objects. And also there are a bunch of helper methods. For example, the length is, of course, an operation that is available on any array, regardless of its type, even in Java. But there's no way to express that in the Java type system. Like I said, they implement the standard collection interfaces, which is also quite convenient. An array is also a list. It's also enumerable. So you can just, this is particularly nice if you just want to return an empty list. If you want to return an empty list, you just return an empty array instead of allocating a whole list object. And then there's something that really bothered me a lot about Java when we started using Java, way back in 1997. And that's the fact that when you have these big array initializers in your code, it generates a lot of code. Java-C generates code to initialize the array instead of just saying, here's a resource in the class file, use that And .NET has this method called runtime helpers.initializeArray, which will basically load some constant from your module and copy that, or an address to the constant, and copy that into an array. And if you're on a big endian system doing the conversion. And they also have buffer.block copy, which is also kind of weird, but interesting. Unlike Java, .NET does not try to protect you from little endian versus big endian differences. And in general, they are a little bit less careful, or intentionally maybe less careful about trying to hide every little detail from the underlying platform, which I think can be a bad thing, but it's also nice to be able to go down to the bare metal when it's necessary. So buffer.block copy allows you to copy some range from a primitive array to another array, and it doesn't have to be the same type. So you can just take a byte array and copy it into a double array. And it will do all the checking, of course, so you cannot run outside the byte array, but converting bytes to doubles is a type-safe operation from a security point of view. It's not type-safe from the semantic point of view, of course, because it means something different. And you also have to deal with big endian and little endian at that point. But if you want to, you have the freedom to do that. A little bit about string. Java 8, or I should say JDK 8, has recently seen a change to the string implementation. The sharing of the underlying character buffers has been removed. .NET went a little bit further, and they actually have strings that are basically like arrays. It's just a variable length object. So when you call a string constructor, it's not a regular constructor, but it's actually special cased by the runtime, and it looks at the length of the string you want, allocates that much space, copies in the data or initializes the data, and returns you a single object containing the string content. And that's, well, as you can see, on a 32-bit system, it's quite a saving for a short string, of course. The overhead goes from 28 bytes to 14 bytes. And of course, there's a level of indirection that is gone. So I think this is a very important performance optimization. There is a theoretical problem with Java JNI. I have never run into it. IKVM obviously uses native strings on .NET, so this is one area where IKVM is theoretically incompatible in JNI. In Java, you can create a string object in JNI using allocate object, and then call the constructor on the object to initialize it in 2 steps. No one does that because it doesn't really serve any purpose, because there are much more convenient JNI functions to create a string like new string UTF. But in theory, it's possible. And in that case, if you go with an implementation where you have a single object, well, if you allocate the object, then there's no way to resize it later unless you play with the garbage collector. So this would be possible. For IKVM, it's not possible to implement that. For Hotspot, for example, it would be possible to implement it. It would be ridiculously expensive because you would have to go through the whole heap and replace the object essentially. But you could do it and just say people don't do that. And in my experience is that people don't do this. And I've seen a lot of weird code.
Those are actually 0 terminated?
Oh yeah, that's another clever feature that Microsoft uses.
So in Java, you can make bunches of zeros in your string. So that
Okay, so yeah, .NET also allows that. So this is just an additional 0 at the end that allows you to pass the string to native code and not have to do any copying. So whenever you call a Windows API and you pass a string, they just pin the string object and pass the address of the string. So it's just an optimization at the cost of 2 extra bytes per string. I'm not entirely sure they still do that, but I believe so. Already touched on this a little bit. They have reified generics, which is very important for performance in their scenarios. I'm not sure if this is the right place to mention, but this is going to be a topic that comes up a lot. The focus difference between Java and .NET couldn't be more different, even though the platforms from a high level look very, very similar. They have a very different focus in terms of optimization and priorities for development. Hotspot is all about dynamic stuff. Other Java VMs are necessarily doing the same things, because the patterns, of course, match with the whole ecosystem and traditions in the Java space. And then there's, of course, all the dynamic languages now coming online or already online, but even more now with Invoke Dynamic on the Java virtual machines. Whereas .NET focuses very, very much on static compilation, not doing any runtime optimizations other than straight jetting and straight inlining and stuff like that. No hotspot type of recompilation or things like that. They really focus on getting the working set down of the code. Instead of trying to make it run as fast as possible, they try to make it as efficient in memory usage and in terms of how many pages are touched when you start up a process. So I think this difference is primarily caused by the fact that Java became popular on the server, whereas Microsoft is still focused a lot on the client. And on the server, it makes sense to spend some extra time optimizing your process because it's usually a long-running process. Whereas on the client, you start up lots of different applications, and you also have multi-user systems. For example, on a terminal server, one IKVM user contacted me because they wanted to run the Eclipse Rich Client platform on or they had developed a Eclipse Rich Client platform application, but running this on a terminal server with a couple of hundred concurrent users used just way too much memory, because every single user will have to load up all of the classes, JIT compile all of the classes, and that's all private memory to that user. There's no sharing. And with .NET, when you compile this with IKVM and then run it on top of .NET, you can actually compile the code to native ahead of time, and all this native code is then shared. So this is why generics are very important, to have reified generics, because if you don't have any hotspot type of optimization where you can sort of get rid of the cost of the erased generics that Java has, you need real generics to be able to get rid of that cost. Java is slowly moving towards getting a module system with Jigsaw. I think it's a very important development. I've often thought about what's the worst thing about Java, and in my opinion, there is no doubt about it. It's the class file, and not just the format. The format is horrible, but the fact that it even exists. A class is not a meaningful thing. A class is just a very tiny. It's like having an individual bytecode. It's completely useless. A class is completely useless by itself, and once again, this is more trauma from the early days, 1997, when we didn't even have jars and we didn't have zip files. We had to load individual classes over HTTP 1.0 connections when we ran our applets, and it was horribly slow. And the fact that we still suffer from things like the fact that inner classes are not a first-class concept in the VM is just, well, to me it's unbelievable. It's ridiculous. It's almost every week on the mailing list that people are saying, when you check in a patch for OpenJDK, please make this method not private but package private to avoid the accessor method for the inner class. That's just horrible. And then other things that are wrong with the class file format, I think, is the limitations, the bytecode size limitations, and the constant pool size, the string literal size, the fact that there is no way to have array initialization, as I mentioned earlier, the fact that there is no first-class support for try finally is something that really is very, very weird now. Back when Java came online, there wasn't that much experience with all this exception handling stuff, and catch throwable, open curly, close curly was a accepted practice. But nowadays we know that you have probably 10 times as many finally blocks as you have catch blocks. So it's very strange that the class file format doesn't have a finally block. the JSR construct in the class file that previously existed and now has finally, thankfully, been eradicated, was a way of getting some of the idea finally in there, at least sharing the code. But that also should have sort of been a wake-up call for maybe we need something else to represent that. And it may seem like sorry.
Don't forget the go to it. Maybe 25% of the compiler code in Jira could be a constructor's control flow that was lost.
Yeah, exactly. It may seem like a small thing, but it makes a lot of sense to have finally natively represented, and that's what .NET does. They also have a fault construct, by the way, but their exception handling is overly complicated and modeled on the Windows model, and therefore kind of slow. So it's not that great. However, back to the module system, the CLR does have a really great module system, and I think that Jigsaw should be able to learn from that. It works very well. It has been in use for, well, almost 12 years now, or 11 years now, and it has evolved a little bit, but not that much. And so I think there's something to learn there. And one thing that they have that is maybe not completely related to the module system, but it is the internal access modifier, which is sort of similar to what Jigsaw is going towards with the system of exporting packages or not exporting packages. But I'm sort of leaning towards saying that it would be nicer to have this at the Java language level with an access modifier instead of having to later on decide what to export or not. But it's hard to make these kinds of changes in existing system. I realize that. Another thing they have, and I would like to argue for, is a metadata API. As I've been saying, I don't really like the class file format, so I would like to see the option of moving away from the class file format at some point. Currently, that seems like it's almost impossible because there is so much code out there that depends on the class file format, that parses class files and does stuff with it. If we have something like ASM in the core libraries and people start using that instead of their own parsers or their own version of ASM, then it might become feasible at some point in the future to move away from the current class file format and retain the API surface to communicate with the metadata. So something like reflection, but then suited for compilers, is needed. .NET has this. It's unfortunately a native API, so that's also a really stupid thing. But in Java, I think there are lots of nice APIs for processing class files. If you just take one of those, add it to the platform, make sure that the abstraction level is high enough that we hide the fact that there are class files, just classes, and expose everything integrated nicely with Jigsaw so that it knows about modules. Make sure it's not tied to the runtime. That's also an important lesson from .NET. You want to be able to compile code that is not written for your current runtime. But other than that, so as a transition path, hopefully to some other format than the class file format. And I would argue for a format based on the module system. So because a class is meaningless, don't try and redesign a new class file format, but design a module format. A module is something that makes sense. A module is a reusable component. It has much more meaning, much more. It's much more useful as a thing to ship around in an individual class file. And so NGen is native image generation, which is it's part of the magic. That's not really magic. It's quite trivial. Well, not trivial. It is the ahead-of-time compiler that Microsoft uses to compile managed modules into native code. And the primary reason for this is, as I mentioned, is working set. If you look at Hello World, now Hello World is not very exciting, but this is a Java Hello World system, outprint line Hello World. This is a C# Hello World, console.writeLine Hello World. The private working set, which is arguably the most important one, is for Java 7, 64-bit Java update 4 is about 7 megabytes, whereas the .NET 4.0 version uses 2.5 megabytes. If you stop and think about that for a moment, it's both of them are completely bizarre, of course. Oops, sorry. But onto a real-world application, swing set 2. So here is the pattern is continued, and you see that swing set 2 takes about 210 megabytes of working set, private working set, whereas the swing set 2 version running on top of IKVM, compiled again with NGen. So this is cheating, I fully admit that. Only takes 63 megabytes. Of course, we're running swing set 2 on top of IKVM, on top of .NET. So the real test would be to write some equivalent application in .NET and then see what the working set was. It would probably be a little bit less because IKVM, even though I'm really great, adds some overhead. This is an interesting tiny little detail that I wanted to point out, but it gives you some idea of some flavor for how far they went in optimizing for this static compilation scenario. These are two C# applications that look should look familiar to any Java programmer, and they look like they should do the same thing, but they don't. They're different, semantically different. So here you have a static type 1. This is a static initializer in C#. And here you have a static field that is initialized with a call to a static method. So if you run, both of these programs have an empty main method. If you run both of these programs, then one of them, this one, will always print hello from init. This one, it's up to the implementation to decide whether or not to print anything in this case. So I think it's kind of bizarre the way they surface this up to the C# world, but at the VM level, this type actually gets a flag in the class that says before field in it, and that means that the runtime has more flexibility when to initialize the static fields. It has to initialize it before the fields are accessed, but other than that, it can do it earlier or later. So it doesn't necessarily correspond to when you run a static method or when you instantiate the thing. And this means that if you run a ahead of time compilation, you can omit the check for the initialization from all of the static methods. You only have to do the check when you access a field. Or you can even run it eagerly when you load the module. So upon module load, you can run all of these things. So this decision can then be made more efficiently by the ahead of time compiler. .NET obviously has no JNI, but it also doesn't have anything equivalent to JNI. It has a hosting API, so it allows you to instantiate a runtime from your C code and do the same sort of thing that the Java hosting API does, but there is no stuff like in JNI you can instantiate objects or do reflection or call methods and all that from native code. But in .NET that's all essentially missing, and the way they deal with this is they added a whole bunch of stuff on the managed side of the world. So you have a class called Marshall that has ways to convert value types essentially to native code, or to convert a native pointer into a value type, or delegates, which are a function pointer, into a native function pointer. So if you want to do a callback from your native code to Java or to .NET, you can do that. You just pass in a delegate to the native code, and then the marshaller will generate some x86 or whatever platform you're on machine code to do the conversion and marshal the code, the system back into the managed world and pass the parameters in. You only have to take care of the lifetime of the thing by not letting the delegate be garbage collected. They have things like explicit structure layout. So if you declare a value type or a class, you can say, I want the fields in this particular order, or I want the fields in this particular offsets, so that you can map these structures exactly on top of the native structures. making it very easy to interoperate with native APIs directly. They have GC handles exposed, so you can, this is like the JNI handles. You can just allocate a handle to wrap your object and pass the handle to native code that can then store it or do whatever with it, and later on pass it back to the managed code to unwrap it. And then there's of course unsafe code. They went quite far with this initially. Now they've sort of stopped paying a lot of attention to this, but Microsoft has a C++ implementation that compiles down to MSIL. So you can just take an arbitrary C++ app, a really big one. For example, they compile the whole of Word to MSIL, and it will just run. And you will not have really any benefit. It's going to be slower, and it's not going to get portable, of course, because it's still, there are all sorts of non-portable constructs in there, and it will all use unmanaged data. But there is one benefit to this approach. When you want to take some code and interoperate, it is much cheaper to interoperate within the virtual machine than to go across the boundary. So if you have some, for example, if you want to use the zlib code in .NET, you could compile the zlib code into IL and then call that directly from your native code. And that might, even though the code itself might run a little bit slower than the natively compiled code, you might gain the performance back because you don't have as much overhead when calling the thing, essentially zero overhead. Everyone here is familiar with annotations, I guess. Java annotations were copied, I think, from custom attributes in .NET, but they made a big mistake or omission. The JSR 175 proposed final draft said, these annotations do not directly affect the semantics of a program. And that's, I don't know why they were so against that, but in .NET they affect the semantics of a program a lot. A good example is a thread static. I think this is a very elegant way of declaring a thread static. So the runtime sees this attribute and then does all the magic needed to turn this into a thread static. So instead of having to allocate an object like in Java and do it.
Isn't that the same thing though? I mean, under the covers?
Sure, under the covers it's the same thing, but for me as a user it's much easier. Yes?
So just, this is a commonly misinterpreted statement.
Okay.
In spec. So let me add a little color. So it is not the case that annotations cannot affect the semantics of a program. It is possible to bake the semantics of certain annotations into the Java language specification. What the spirit of this this statement, whether you agree with it or disagree with it, is that if you're going to use annotations to carry program semantics, it needs to be part of the programming language specification. It's not something that is acceptable to inject in via a tool, and that's what this statement is getting at. It probably doesn't change whether you agree with it or disagree with it, but it's a commonly misunderstood point.
No, that does change it. Well, maybe I want to rephrase the VM specification, I would say, then in this case. Because that's also one of the nice things about this. Of course, .NET wanted to be the common language runtime supporting multiple languages. This mechanism makes it so that as a language implementer, you don't really have to care about adding anything for that. As long as you support this custom attribute notion, then you get all the runtime features for free. Another feature is the ability to call native code directly. So you say DLL import the name of the DLL. You add an extern modifier to your method, and this name will then be looked up in this dynamic library, and the return values in the parameters will get marshaled automatically. Another one is security critical, which I'll get back to. And here's the layout kind thing, the layout and field offset I mentioned earlier. So here's a value type from IKVM JValue. This is from the JNI implementation, where I'm creating a union type of all these Boolean, bytes, character, short things, and they all live at offset 0 in the field. So it's easy to create a union. And this is even verifiable, so as long as you don't have an object reference in there, you can just overlay fields like that. like I said, they don't really care about protecting you from big versus little engine. Yes, Joe?
Another comment on annotations, the more precise statement that was made around the time that the file is that annotations do not affect the generated bytecode for methods of the annotated structures. However, it's possible for a class to load the annotations on itself. So a class can load its own annotations, which include things like byte arrays, which you can then throw into a class loader. So you can still subvert the spirit of this by having executable code created based on the annotation values on a class.
Anyway, so mainly my point is, I think this is a cheap mechanism for adding features to the VM without having to go through a lot of design on the language front, which language design is very hard. Adding features to the VM is also hard, but it's in many cases not as hard as actually designing a good language feature. And in this case, you can sort of take a cop out and say, okay, we'll add the feature, and it'll be a little bit more ugly than a language feature, but it'll work. So finalization. This is an area of Java that well, is also quite controversial. And .NET copied it initially. They just copied the Java finalization stuff, and then they realized it didn't work all that well, like people in the Java community realized. And instead of adding something like phantom reference, which is Java's sort of answer to finalization, not working properly, .NET added something called a safe handle or critical finalizer object, which is solves most of the finalization problems. One of the problems with finalization is that untrusted code can create finalizers. So if I have some idiot code that just spins infinitely in the finalize method, then none of the other stuff will get finalized on many systems. I don't know if actually I have not looked into this recently. Does anyone know? Are there multiple finalizer threads now? No.
We did, if I remember correctly, yes.
Okay. But anyway, so what they did is they added a second type of finalizer that is trusted. So you can only implement the critical finalizer object if you are trusted, fully trusted. And these are treated separately by the GC. So first the normal finalizers are run, and then after those have been finalized, the critical finalizers get run. And I don't mean that in the sense of running them in that order, but I mean in terms of reachability. So when your critical finalizer object when your outer object is reachable, your critical finalizer will not be reachable. So a more concrete example would be, I know that in Java, there's been a lot of stuff going on now with, is it file input stream and all that finalization stuff. What they do is they have basically file stream, because they had the same problem in .NET. They have file stream implement finalize, and they call close in themselves. But file stream itself does not own the native resource. They just have a field that is of type critical finalizer object that owns the native resource. It's also a safe handle, which is a subclass of this. So, and this thing encapsulates the actual operating system handle that corresponds to the file. So when the system starts finalizing the file stream, the close method gets called, the file gets flushed, but because these things are finalized in order, you don't run the risk of closing the handle before flushing the stream. So this solves that problem, and it also solves the problem of when you want to unload your code from an environment where where you want to provide high reliability. You can basically say, okay, I'm only going to run the critical finalizers and not the other ones. So you can free all the handles without running the risk of untrusted code. I'm already out of time. One other quick thing I want to mention is the tool support. I think it's been really beneficial on the .NET platform to have a textual representation of the assembly format of a module. So you can take any .NET module, you can disassemble it, you get one text file and a bunch of resource files, and you can reassemble it. And the fact that this is standardized, there are all sorts of Java assemblers and disassemblers, and I'm looking forward to today's talk about AL1. But there needs to be a standard format, I think, to be part of the ecosystem. And also another interesting tool is PE verify, which calls the verifier in a static ahead of time way just to be able to check your module. If you're a compiler writer, it's very nice to just take a file and run it through the verifier. These tools, of course, also exist for Java, but it's nice to be able to run the actual verifier that's in the runtime and not some other implementation. Are there any Java applications left? Sunmisk Unsafe has become part of the public API, effectively, I'm afraid to say. Who here has used Sunmisk Unsafe outside of the JDK code? Yes, exactly. So in .NET, this is just to give you an idea. This is most of the Sunmisk Unsafe API. Everything has a public equivalent in .NET. So these things need to be public and well designed. This is a straw man proposal. I'm going to skip that. Skip this as well. Yeah, this is something. Java has a lot of security vulnerabilities, if you have noticed this. .NET also has a share, but they have an interesting concept here, and I think Java can learn from this. They separate their code into transparent code and critical code in terms of security, and safe critical code. And safe critical code is the bridge between the two. You cannot call from transparent code into critical code, and critical code is the only code that can do trusted operations. And this separation means that when you audit your code, you know where to look, because you just look for the safe critical annotation, and when you see that, you know that you have to do a security audit on this code. Okay. On the Lambda static versus virtual extension methods, I want to add a few words, because here I have a very strong bias, because virtual extension methods are going to really suck for IKVM. And I want to, and I'm probably not going to change your mind, but I want to say something, argue some case for static extension methods. Virtual extension methods are really nice, but static methods have a very nice added feature in the fact that they're composable. And you're not stuck with them for all eternity. Virtual extension methods will forever and ever clutter up the interface. And that's just something I wanted to say.
There's actually two dimensions to it, right? There's a static versus virtual dimension, and then there's an orthogonal dimension, which is use site versus declaration site rejection. So your second point really has nothing to do with static versus virtual as much as, because we could do declaration site static extension methods, and you'd be just as annoyed.
Right, yeah, true. Okay, thank you.